In this video, I'll do a quick overview of the important concepts that are presented in Chapter 17, which primarily deals with electric forces and electric fields. Now, I do want to point out that a lot of this information you will need to know for the closed book portion of the midterm exam. So let's start off with the structure of the atom. Now, this is a very simple model of the atom, but here are the key properties that you need to know about the atom. The nucleus contains protons, and they will always have a positive charge. Nucleus also contains neutrons, which have no charge. Then we come to this part where the nucleus actually accounts for about 99.99% of the atom's mass. And finally, the nucleus is very small. Let me give you an analogy. If you were to look at a period in a sentence, and that represented your nucleus, then your entire room would represent the electron cloud where the electrons reside. So now let's look at this electron cloud. It contains electrons which have a negative charge. The electrons can leave the atom. Protons and neutrons cannot under normal circumstances. Another thing to note, metals are a good conductor of electricity because the electrons within the metal atoms can easily go between one another. So in other words, the metal acts as though it exists in a sea of electrons. So the electrons have a lot of mobility. Nonmetals are poor conductors of electricity because the electrons are tightly attached to their atoms. So there's no easy sharing of electrons between atoms. Consequently, nonconductors are good electrical insulators. For example, the plastic covering over a light switch. Another thing about the electron is it has a very small mass, and that's one of the reasons why it can leave an atom and go to another atom. However, the electron does account for the volume of the atom. So the volume of all objects is due to the electron cloud. Now here's something else you should know, and that's called the charge law, or rule. And it goes like this. Unlike charges attract. So positive and negative charges will always be attracted to one another. So two positive charges will repel one another, two negative charges will repel one another. Another thing to note about charges is objects develop a positive charge by losing electrons, objects develop a negative charge by gaining electrons. Only electrons can move between atoms. Now we come to an important thing here that you should once again know for the midterm exam. We have a new unit called the Coulomb, and this represents a unit of charge and is represented by an uppercase C. So it turns out that a single electron or a single proton has a charge of 1.60 times 10 to the negative 19 coulombs, and the only difference is the electron has a negative charge, the proton has a positive charge. Another thing that you need to know for the closed book part of the midterm exam is that we have another conservation law. This time it's the conservation of charge. So imagine this. You have a system, and in this system you have two objects. Let's call them A and B. Both objects are neutral, and what that means is the number of electrons and protons on each object is the same, so their net charge is 0. For the system as a whole, the net charge is 0. Now let's say that we take A and B, we rub them together, and 10 electrons leave object A and jump onto object B. Well, now object A has a positive 10 charge, while object B has a negative 10 charge. But the system as a whole is still 0 charge. So this is a demonstration of the conservation of charge. Here I wish to quickly discuss Coulomb's law for point charges. This formula will allow us to calculate the electrostatic force between two charges. In the lecture notes, I show you how to use the vector form of this formula, which is shown here. However, in another video, I show you how to use magnitudes to perform this calculation. Some students may find it easier to work with the magnitude form of Coulomb's law. For now, I want to point out the key features of this formula. First, we see F sub 1, 2. You are to read this as the force on charge 1 due to charge 2. If it was F sub 2, 1, then it would be the force on charge 2 due to charge 1. So whatever number or letter that appears first in the subscript is the object that is being acted upon. Second, we have a special constant called Coulomb's law constant, which has a value of 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. Third, we need to know the value of the charges in coulombs as represented by the Q sub 1 and Q sub 2. And finally, we need to know the distance between the two charges in meters. Do not forget to square the distance. Now I want to point out the r with the caret over it. This represents the unit radius vector from charge 1 to charge 2. How you use the unit radius vector with the formula shown here is explained in the lecture notes. As I said before, there is a simpler looking formula which uses magnitudes only, which you may prefer to use. The calculation method using magnitudes is covered in another video called Coulomb's Law Magnitude Form. Now I'm going to go over this example here because you have to understand how to determine which way a force will act on a charge due to another charge. But first of all, I want to introduce you to a new prefix called mu, which represents 10 to the negative 6 power. So in a lot of calculations involving forces between charges, you're going to see something like a microcoulomb. So 30 microcoulombs is really 30 times 10 to the negative 6 coulombs. So here I have two charged objects, Q1 and Q2, and what I want to do here is just simply show you how to determine the direction of the electrostatic force acting on an electron which is placed at position A, B, or C. Alright, let's study the interaction of the electron when it's at position A. First of all, I want to point out that you have two choices in the direction of the force. Either the electron can be pushed towards the left or pulled towards the right. This left or right action here is going to be the line of action. Now, if I got an electron which has a negative charge at A, and I look at Q1 which has a negative charge, I know that is a repulsive force. Therefore, Q1 is going to push the electron at A to the left. That's going to result in a force at A due to Q1, which I've drawn an arrow here to indicate. Now we have to look at the force exerted on the electron due to charge number 2. Once again, this is going to be a repulsive force, so charge number 2 is going to push the electron to the left. So once again, I have another force, and that would be the force acting at A due to charge 2. Notice I've drawn my two arrows, but because the force due to Q1 is a larger force, the arrow is longer. But overall, the net force from these two charges is going to push the electron towards the left. Now let's look at the interaction if I put the electron at point B. Well, first of all, charge Q1 is going to cause the electron at point B to be pushed towards the right. Therefore, I draw an arrow and I have it labeled as the force at B due to charge 1. Charge number 2 is going to push the electron at point B to the left. Therefore, I draw an arrow and I have a force at B due to charge 2. And since these two forces have the same magnitude of charge and the distance between these two forces and the electron is the same, the length of the arrows are the same. So for the electron at point B, the two charges cancel one another. The net force on the electron at point B would be 0. When I look at the electron at position C, basically it's just like what we had for position A. The only difference now is the force are now acting towards the right. So here is an example from your lecture notes. All I want to do is explain some of its key features. Now, if you have already read this example, you know the calculations may seem intense and time-consuming. Well, I have good news for you. On the open book part of the midterm exam, the configuration for the 3 charges will be linear. Please check out the midterm lecture exam review for some example calculations. In this diagram, which is not drawn to scale, you have 3 charges. Note, for each charge, its charge and location are given. The minute you see microcoulombs, you are to rewrite micro as 10 to the negative 6 power. All locations must be in meters. Now, I am not going to go into detail on how to solve this problem, since it is covered in the lecture notes and Coulomb's Law magnitude form video. However, I do want to stress the following. First, because some of the distances between charges, for example Q1 and Q3, are diagonal, you will need to use Pythagorean's theorem to find the distance between charges. Second, you should know some basic rules of geometry. Check out Some Basic Rules of Geometry document located in the Chapter 17 folder. And finally, look for the symmetry in these types of problems. Physicists love symmetry. Why? Because once you know the property of one symmetry configuration, then those properties will carry over to the other configuration with only slight changes needed. So for the diagram, I recognize I have two identical right triangles. Therefore, once I know the distance between charges Q1 and Q3, I know by symmetry that the distance between charges Q2 and Q3 is the same. Now we move from electrostatic forces to electric fields, which are created by charges. But to understand what an electric field is and what it does, we will return to gravitational fields. In Physics 1, we discussed Newton's law of gravitation. We learned that two objects will always have an attraction between them, and that the strength of this force, or attraction, is directly dependent upon the object's mass in kilograms and inversely dependent upon the distance in meters between the two objects. So I have rewritten the formula for calculating an object's weight in newtons to one showing the calculation of the gravitational field strength, that is, the G value. In Physics 1, the G value was 9.80 meters per second squared, because all action took place near Earth's surface. However, if you were to leave Earth's surface in a spaceship, you would notice a decrease in the G value. Now let us focus our attention on this diagram and how to interpret it. I have Earth being represented by an uppercase M, because relatively speaking, Earth is a massive planet. The black dot represents an exceedingly small mass, for example, a ball. We know that a ball released from rest will fall towards Earth's surface, and if we ignore air resistance, the ball will travel in a vertically straight line to the surface. This is what the arrows are indicating about the ball's motion. The arrows are all pointing to Earth's surface. The arrows represent Earth's gravitational field. The field lines are telling us which way an object with mass will move when released from rest. Notice how the arrowheads are closer to one another while the arrow tails are more spread out. As the field lines come closer together, the field strength, that is the G value, increases. Now let us apply what we have learned about gravitational field lines to electric field lines. Let me first explain the two diagrams. Unlike gravity, which is always an attractive force between objects with mass, charged objects can be either positive or negative. Consequently, we need two types of arrows to indicate the two types of charges. So here is the rule. Positive charges will always have arrows, that is, electric field lines, leaving them. Negative charges will always have arrows entering them. Now here is what is important for the homework assignment and the closed book part of the midterm exam. If you are given a charged object but not its charge, for example the positive Q or the negative Q in the diagram, then you can still determine the sign of the charge by looking at the direction of the arrows around the charged object. In addition, the strength of the electric field is indicated by the number of lines around the charged object. As the number of electric field lines increases, the electric field strength increases. Real quick note here. If I show you an object which has no electric field lines around it, then the object is neutral. That is, the number of electrons and protons are the same. Also note there are two things electric field lines may not do. First, the lines can never cross one another. Second, a charged object cannot have electric field lines, that is arrows, which are both entering and leaving the object. All of the above I just mentioned will be important information for the homework assignment and the closed book part of the midterm exam. Before I forget, I want to explain the black dot. The black dot represents a small test charge which can be positive or negative. In a formula, the black dot is represented by the Q sub naught. When I say it is a small test charge, I am not referring to its mass, but to the amount of charge it has. So, we commonly use an uppercase Q to represent a charged object that is creating the electric field. The small test charge also creates an electric field, but its field strength is small compared to that of the uppercase Q. Now, let me relate the formula you see here to the one we were just looking at for gravity. Once again, we have a force, but it is an electrostatic force. The test charge corresponds to the mass m in the gravity formula. The E vector represents the electric field strength in newtons per coulombs and corresponds to the gravitational field G in the gravity formula. This formula tells us that if we place a small test charge in the electric field E, then that test charge will experience an electrostatic force given by Coulomb's law, which will create an attractive or repulsive force between the uppercase Q and the test charge. To determine if the force will be attractive or repulsive, we just apply the charge rule. So, let's assume the black dot is a small positive test charge. If I were to release the test charge in the top diagram, then it would experience a repulsive force pushing it away from positive Q. If I were to release the test charge in the bottom diagram, then it would experience an attractive force pulling it towards Q. So here, we have examples of how the electric field lines, that is the arrows, relate to the type of charge and magnitude of the charge. Since both charges are positive, the field lines must point away from the charged object and they are not allowed to cross one another. The object with the larger charge has more field lines. Now we are looking at how electric field lines interact between two charged objects. Notice how a positive charge has arrows leaving it while a negative charge has arrows entering it. Also, at no time do the electric field lines cross one another. If the magnitude of the charges is the same on both objects, then you will have perfectly symmetric lines. So quickly, I want to point out this formula which is used to calculate the electric field strength at a specific point called A due to charge Q. Formula tells us that the electric field, just like the electrostatic force, is a vector quantity. And when you look at this formula, you should see a similarity to Coulomb's law formula. Once again, this formula is in vector form. However, the video, Electric Fields, Magnitude Form, will show you how to perform the same calculation using magnitudes only. So, you can have several charges, each creating their own electric field. Since the electric field is a vector quantity, you can add them vectorially to obtain a net electric field for a specific point. I want to emphasize the black dot is an imaginary marker. There is no real object, charged or neutral, at this location. What you would do in a problem like this is calculate the electric field at point A due to the two charges, and then vectorially add the fields to obtain a net electric field at point A. Quickly, I want to show you how you can determine the direction at point A of the electric field due to each charge. Since point A is on the x-axis, the direction of an electric field due to a charge can only have one of two possible directions: positive I hat, that is, pointing to the right, or negative I hat, that is, pointing to the left. Please note there are other electric field lines leaving the charged object, but they are in different directions and so do not affect the electric field at point A. Looking at charge 1, which is a negative charge, I draw the following two electric field lines. Remember, for negative charges, the field lines are always entering the charge. Notice the field line on the right side is covering point A. Therefore, the electric field line direction for charge 1 is in the negative I hat direction because the arrow is pointing to the left. Looking at charge 2, which is also a negative charge, I draw the following two electric field lines. Notice the field line on the left side is covering point A. Therefore, the electric field line direction for charge 2 is in the positive I hat direction because the arrow is pointing to the right. After assigning directions to each charge's electric field magnitudes, you add them vectorially to get the net electric field strength at point A. Here is a formula to calculate the electric field strength between two parallel plates. I will go into greater detail about this formula when I discuss capacitors in Chapter 18. I briefly want to discuss what the electric field is like within a metal conductor, whether the conductor is a solid, like a wire, or a shell, like a metal garbage can. In both situations, if the conductor develops a charge, positive or negative, the charge will quickly redistribute itself to the conductor's outer surface. This occurs because each individual charge creates an electric field which interacts with the other charges. So, the net effect is all charges move to the conductor's outer surface, resulting in an electric field of 0 inside the conductor. Wait a minute, Mr. Riley. Why is the electric field 0 inside the conductor? Remember, the electric field is a vector quantity. So, look at this situation here as a quick explanation. These two positive charges have the same magnitude of charge, but the electric field lines pointing inwards are in opposite directions and therefore cancel out, that is, give a net electric field of 0 inside the conductor. Now let me tell you the safety aspects of this effect. If you find yourself outside during a thunderstorm, then you want to take shelter in a metal shell because the electric field from the thunderstorm cannot enter the shelter. Therefore, you cannot be struck by lightning, assuming you do not have some metal rod from outside entering your shelter. To understand what these diagrams are showing, imagine the circle in figure A represents your view of looking down into an empty soup canister. Currently, the metal canister has no charge. That is, the number of electrons and protons is the same, or in other words, the canister is neutral. What I have done in figure B is to take a positive charge, attach it to a stick, and insert it inside the canister, but never touching the canister walls. The electrons in the canister wall are pulled in the direction of the positive charge. This causes a removal of electrons on the outer wall, giving the outer wall a positive charge. However, the net charge on the canister is still 0 because no electrons have been removed or added. The electrons have only been shifted from their neutral position. Figure C is figure B, but with the electric field lines drawn. This diagram shows how a metal conductor's shape affects electric field lines surrounding it. By looking at the arrows, we can tell that this metal conductor has a positive charge. On this diagram, there are two regions which greatly affect the electric field line's intensity. They are B and C. Region C has the lowest intensity because the spacing between the arrows is the same from tail to head. Region B has the greatest intensity because the spacing at the tail is closer than at the head. Now remember, electric field intensity is directly related to the electrostatic force it can generate. That is, greater intensity creates a greater force. So, the sharp corners on metal conductors will experience more electrical discharge, think lightning, than the flat surface of the same metal conductor. You have experienced this whenever you get a shock from a doorknob. The miniature lightning bolt always goes for the tip of your finger. To protect tall buildings from the damage that can be caused by lightning, a lightning rod is placed on the building's roof. When lightning strikes the rod, a good conductor of electricity, a wire carries the damaging charges to the ground instead of having the charges go through the building and its contents.